Okay, in the last lecture we talked about something called an indefinite integral. Look like this. And do you remember what it was? The general antiderivative of f. Okay? It's called an indefinite integral. Today, we're going to do something called a definite integral. Here's what it looks like. Very similar to an indefinite integral, with one small visual difference. There will be numbers here and here. Okay, let me put A and B. Those would be numbers, not variables, okay? So you wouldn't actually see letters there. You would see numbers there. I'm just using letters to stand for those numbers. Okay? That would be called a definite integral if there are numbers above and below the integral symbol. Okay, now, what does a definite integral tell you? It tells you, just like an indefinite integral tells you the antiderivative of f, a definite integral tells you the area, the actually signed, I'll explain that in a minute, the signed area, and then here's another word, under the graph of f. I want to shrink this down a little because I would like to write that all on one line. Okay, so let me explain to you what the word signed means, and let me explain what I mean by under the graph of f. That's not a difficult concept, under the graph of f. You probably think, why do you have to explain that? Because it doesn't mean necessarily what it sounds like. Sometimes the area under the graph of f is actually above the graph of f. I know that seems confusing, and that's why I want to explain it. Okay, so let's do the under part first. When I say under the graph of f, what that means is between the x-axis and the graph of f. Okay, so if you have a graph that does something like this, let's pick blue as a color here. So if you have a graph that does something like that, then the area under the graph, the area under the graph would technically be this area up here, which is not under the graph, is it? It's above the graph. But nonetheless, that's just what we call it. The area between the x-axis and the graph of f is called the area under the graph of f. If you have a graph that looks like this, then the area under the graph makes a lot more sense. And if you had a graph that looks like this, then some of the area under the graph is actually under the graph, and some of the area under the graph is actually above the graph. Okay, so again, when we say area under the graph, that's just a term that we use to mean the area between the x-axis and the graph. Okay, now what about the word signed? What does that mean? That means that the area could be positive or negative. So we're not in high school geometry anymore where we say areas always have to be positive. Okay, this is a signed area, which means it can be positive or negative. And here, how do you decide? You decide like this. Above the x-axis is, let me add a word, let's say area above the x-axis is considered positive. I'm going to erase this other sentence so that we can use this room. Okay, area above the x-axis is considered positive, and area below the x-axis is considered negative. So in the picture at the left, this area up here would be positive area, and this area down here would be negative area. And negative area does cancel out positive area. Okay? So you could have a lot of shaded area and at the same time say the area is 0, because you might have the same amount of positive area as negative area and they could cancel each other out. Okay? All right. Go back up to that sentence, the signed area under the graph of f. I want to add one more phrase to that. Okay, let me erase this now so we can use this room if we need it. So I want to add a phrase. I'm going to erase that period at the end and add a phrase. From x equals a to x equals b. Okay, so in this case, let's just keep the same picture, but let's put here on the x-axis, let's put a here and b here. Then the integral of f from a to b, that's how you say this, the integral of f from a to b, all right, would be measuring this amount of area. Starting at a on the x-axis and stopping at b on the x-axis. Okay, so that's what a definite integral is. I'll point out to you, when I read that out loud, I didn't say the word definite, did I? So here's how it goes. When you look at them, you can tell if an integral is indefinite or definite based upon, are there numbers here or not? No numbers is an indefinite integral. These numbers, by the way, they're called limits of integration. So visually, you look at the integral. If there are no limits of integration, then it's an indefinite integral. If there are limits of integration, it's a definite integral. So you can tell by looking immediately if it's indefinite or definite. Okay, now common practice, when you read it out loud, you don't see if there are limits or not. Like what I'm saying is, pretend that somebody has this written on a piece of paper. You can't see the piece of paper. Maybe you're talking to the person on the phone and they're reading to you what's there. Then you wouldn't be able to see if there are limits of integration or not, right? So you might say, so they would have to tell me if it's an indefinite or a definite integral. Well, the truth is, even then, we don't usually say the word indefinite or definite. What you do is this. If somebody says the integral of f, then you understand that that means an indefinite integral. If somebody says the integral of f from a to b, then they are mentioning limits of integration, so then you know it's a definite integral. Okay? All right, now point out a couple of more things. An indefinite integral gives you what kind of answer? It gives you an answer that is a function. A definite integral gives you what kind of answer? It gives you an answer that is a number. That's important, okay? Also, if you look at this description up here, an indefinite integral is an antiderivative. A definite integral is the area under the curve. And yet those are both called a name that is almost identical. And when you write them down, they look almost identical. So that seems a little bit strange, maybe, that, one second, these look and sound almost identical, but their definitions are totally unrelated to each other, it seems, right? Why in the world would the antiderivative of a function and the area under the curve of a function both have the same symbol almost and the same name almost? Because what does the antiderivative have to do with the area? Doesn't seem like they're related at all, does it? Well, that explanation is going to wait until the next lecture. They're actually very, very closely related, but it is not obvious how. And I'm going to put that discussion off for one lecture. The only thing I want to do today is show you how to calculate that area under the curve. Okay? And you'll see that it involves the antiderivative, but if it's okay with you, I'm not going to explain why until the next lecture. Okay? All right, so how to calculate definite integrals. Let's look at this picture straight out of the book on page, one second here, what page is this? 230. Okay? It shows a portion of the graph. That blue line is from the equation negative 32x plus 48. Okay, now let's calculate a few definite integrals. We can do this without any special knowledge because it's just going to involve areas of triangles. Okay, this intersection with the x-axis, by the way, in case you can't tell, that's at the number 1.5. Okay, now, what if I said, this is the proper words we would use. Integrate negative 32x plus 48 with respect to x from, let's go from 0 to 1.5. Okay, then that is simply asking us for the area right here. That's just a triangle, right? The height is 48 and the width is 1.5, so you can calculate that without any special knowledge. It's 1/2 times the height times the width. And that would be 36, correct? Let's integrate from 1 to 1.5. What area would that be? That would be right here. Again, that's just a triangle. What would the height be? The height would be 16, and the width would be 1/2. And so that area would be 1/2 height times width. That's an area of 4. Let's integrate now from, let's say, 2 to 3. Okay, so that would be this area. Okay, now what shape is that? That's a trapezoid. What's the area of a trapezoid? The area of a trapezoid is just the average of the length of the parallel sides times the distance between the parallel sides. So let's figure that out, okay? This side over here, how long is that? If we plug in 3 into our function, we'll get negative 96 plus 48, which is 48. How long is this side here? If we plug 2 into our function, we get negative 64 plus 48, which is a length of, well, that would be negative 16, right? So this is a length of 16, right? And the distance between the parallel sides is a distance of 1. Okay, so that area is the average of 16 and 48, which is 32, times 1, and so that's an area of 32. But it is below the x-axis, and since we're doing signed area, that would be negative. Okay, so using the trapezoid area formula, it's negative the average of 48 and 16 times the distance between the parallel sides, which is 1. And so we would get negative 32. Okay? Now let's do one more. What if we wanted to integrate from, how about we'll say 0 to 2? So now we're wanting to find this area. Okay. That's two triangles, right? And by the way, this triangle here, we already calculated that area. It's right here. That's an area of 36. Okay. But let's write it down anyways. It was half times 48 times 1.5. Okay. Now we're going to add to that this area, but this area down in that small triangle is a negative area, so that means we're going to be subtracting some area. Okay? And it's going to be half times 16 times 0.5. Because again, this is 16 and this is a 0.5. Okay, so let's see what we're going to get there. This is going to be 36 minus 4, and so the answer is going to be 32. So you see there's 32 square units of net area there. That is 36 positive units of area and 4 negative units of area. So the net area is 32 square units. Okay, that's the idea. Now, those calculations were very easy because our graph was a straight line, and so we only had to calculate areas of triangles and trapezoids. If the graph was curved, then it would be very, very different. Because how do we calculate areas under curved lines? It all depends. I mean, if it was a nice curve like a circle, then it would be easy, but something like a parabola would be very different. Or what if it's not a well-known shape at all? What if it's just a randomly shaped graph? How would you calculate that area? So this is where we get into the real calculus here. Okay, and this is where we're going to show the relationship between the area under the curve and the antiderivative of the function. So let's go back. I want again to relate this to the indefinite integral. Okay, so let's just touch base with that again. When you calculate the indefinite integral of your function, you get the general antiderivative of the function. So that means you get a function, let's call it capital F of x plus c, where capital F is an antiderivative of lowercase f. In other words, lowercase f is the derivative of capital F. And in fact, I told you that that's how you can check your answer when you do an indefinite integral. You can see if you're right by calculating the derivative of your answer and seeing if the derivative equals the integrand. Okay, so indefinite integral of little f equals capital F plus c, where capital F prime of x equals little f of x. Okay, now for a definite integral, the integral of f of x dx from a to b equals, so I already told you what it means. It means the area, the signed area under the curve of f, from x equals a to x equals b. Okay, what does that have to do with antiderivatives? Well, here's the answer. You find an antiderivative for f, just like you were going to do an indefinite integral. But then what you do is, instead of writing that plus c, you write that antiderivative and you plug in the number b, and then you write that antiderivative and you plug in the number a, and you subtract that second one from the first one. Okay? Now, I'm not going to explain to you in this lecture why this tells you the area under the curve. We'll do that in the next lecture. Okay? But for now, I just want to practice using that. And by the way, there's an intermediate set of symbols that you write down in the middle, and that is this. Let's bump this over. Because there's really two things you need to do here. You need to, number one, find the antiderivative. That's the first step. And then number two, you need to plug in b and a to calculate the antiderivative at b minus the antiderivative at a. So there's really two things you have to do. And generally, you find the antiderivative, and then you're going to want to write that down so that you don't forget it. Or if you're being graded, you want your professor to see the work you've done. So you're going to want to write down the antiderivative and then plug in the numbers b and a. So the way that we do that is we write the antiderivative as a function with no numbers plugged in. The variable x will be still there. And then you draw this vertical bar, and you put the a down here and the b down here. And that vertical bar means I'm going to plug in b, and then I'm going to plug in a, and I'm going to subtract the second one from the first one. So in other words, that vertical bar means you're going to do this. Okay? Now, here's a question that often comes up. Do you still need to put plus c? The answer is no, you don't, but you certainly can if you want to, because look at what would happen. If you wrote the antiderivative plus c, and then now I should put parentheses because there's more than one term. A lot of times people leave the parentheses off. But in any event, if you did that, then when you plugged in the b and the a, you would get this. Capital F of b plus c minus capital F of a plus c. So you would get capital F of b minus capital F of a plus c minus c, and the c's would cancel each other out. So there's no need to write the plus c, but if you feel like writing it, it's not going to give you the wrong answer. It is going to work out the same either way. Okay? All right, so now, taking that into account, let's calculate some more integrals where the function we're integrating is not linear. Let's look at that picture there from the book on page 236. Here the function that's graphed is f of x equals x squared. Okay, from 0 to 3. So let's calculate that shaded area that they're showing. So that would be the integral of x squared with respect to x, from 0 to 3. Okay, What is an antiderivative for x squared? Well, if you follow the rules that we covered in the previous lecture, then you know that would be 1/3 x cubed. Okay, now we're going from 0 to 3, so I write that, and then I write 1/3 times 3 cubed minus 1/3 times 0 cubed. And that gives me 9 minus 0, which is 9. So there is 9 square units of area that is shaded there. It's pretty easy as long as you know how to do derivatives, because the integral is just the derivative backwards. And then you just plug in the limits, and there you go. Okay? Now a couple of rules to cover that are more or less obvious, but I think we should point them out. And these are listed on page 233. Okay? Just some simple things to remember. First of all, you can certainly integrate a function from one limit of integration to the same number. There's nothing wrong with that. The only thing is that when you do that, there is no width to the shaded area, which means there's not going to be any actual area there. The answer will be guaranteed to be 0. Okay? So it's perfectly all right for those two numbers to be the same. Also, by the way, let me say this. We're used to this number, that limit of integration on the top is almost always bigger, and that limit of integration on the bottom is almost always smaller. But there's no rule about that. The top limit of integration can certainly be smaller than the bottom limit of integration. That's fine. And you're just going to end up with an area that is a different sign. Okay? You see, let's look at this. Let's write the integral of f from a to b. Now, let's just do a little bit of work here. Wouldn't that be capital F of b minus capital F of a, where capital F is antiderivative of little f, right? Now, notice, that that's the same thing as writing negative capital F of a minus capital F of b, which would be negative integral of f from b to a, right? Look at that for a second and make sure you agree. And then I'm going to delete the stuff in the middle and shrink that down. Let's collapse this. I don't want to move the whole thing. I just want to move this over here. Okay, that's a very handy rule. So, let's go back to that problem we did a minute ago. The integral of x squared from 0 to 3 came out to equal 9, and I said there's 9 square units of area there. And that's true. I just want to point out that if we had written the integral of x squared from 3 to 0, then in that case we would have come out with an answer of negative 9. I would do it one of two ways. You could either do this, one-third times 0 cubed minus 1/3 times 3 cubed, which would be 0 minus 9, which is negative 9. Okay, that's one way to do that problem. Or another way to do it is to say that's negative integral of x squared from 0 to 3, which I already calculated, and I already know that that integral is 9, and so the negative of that would be negative 9. Okay? So how does that square with the idea that we said earlier? There's 9 square units of area here. Okay? And that makes sense if you look at this. But how does that make sense if you look at this? It's because if you go back to the very top of the notes, the beginning of the lecture, and I said that the one I circled in red is the area under x squared from 0 to 3. In other words, looking forward, you would say there's 9 square units ahead of me. The one I circled in green is the area under x squared from 3 to 0. So that's looking backwards. You would say there's 9 square units behind me, which is theoretically the same as saying negative 9 square units in front of me. Does that kind of make sense? In the picture, I would write 9 there, and I would just say that's positive 9 if you're looking in this direction, and it's negative 9 if you're looking in this direction. But I wouldn't do this. I wouldn't write that, because that's going to be misleading. Because now people who see that are going to say, but it's above the x-axis, it should be positive. So I would just write 9 if I was filling that number in the picture. And then I would say, and then if you're looking in the positive direction, you would see 9 square units. And if you're looking in the negative direction, you would see negative 9 square units. I hope that makes sense. I hope it's not confusing. Okay, here's a couple of other rules. The integral of a function from, let's say, a to b, let's say you added onto that the integral of the same function from, let's say, b to c, starting the second integral where the first one left off. That's the same thing as integrating the function once from a to c. And we actually did that earlier. Let's go back and look at that. Here, when we integrated from 0 to 2, look at how we did that. We calculated that triangle, which was this area, and then we added to that this triangle as negative area. So that's why it says subtract. I said added. If you look at it, you see subtract, because what I said was we add it as negative area. That's this triangle. So we integrated from 0 to 2, but you see what we really did was we really integrated from 0 to 1/2. I mean, sorry, 1.5. We really integrated from 0 to 1.5. And then we also integrated from 1.5 to 2. And then we combined those two triangles into one area. Okay? Now I want to write down two more rules for you, which are not anything new. This is the same as it was for indefinite integrals, which was that you can split them up with addition or subtraction. And you can factor out constants. So those are some very helpful rules. Okay, and that is an indefinite integral. Sometimes you'll see some physics problems that talk about velocity and acceleration and stuff like that. So just to alert you to what's going on there is in physics, you have the position of a particle. I would call that P of t. It's usually measured in time, so that's why I said t. I would call that P of t, but they never do. They always call it S of t. Okay, and then you have the velocity of a particle. We'll call that V of t. And then you have the acceleration of a particle. We'll call that A of t. And the relationship is this. Velocity is the derivative. Here, let's just write it like this. Let's just write d dt. Velocity is the derivative of position, and acceleration is the derivative of velocity, which means that velocity is the integral of acceleration and position is the integral of velocity. So for instance, if you know the velocity of a particle, if they give you a formula for the velocity and they say, how much has the particle moved over 5 seconds? You would just integrate the velocity from 0 to 5, and that would tell you the change in position. Okay? If you know the acceleration and you want to find the velocity, you integrate acceleration to find velocity. Take the derivative of velocity will tell you acceleration, and vice versa. So those types of problems are oftentimes thrown in as practice problems or homework problems, and that's the relationship. Okay? Now, get some practice on just calculating these things, and then after the break, and then next lecture, I'll explain why, because I don't know if you noticed, but I never explained why this formula is true. What does this actually have to do with the area under the graph? I did not explain that. So I'll explain that in the next lecture, okay? But you can go ahead and get practice on calculating these things now.